Hi folks, here we're going to have a look at an example of taking a complex number which is in this normal real and imaginary part. Well, the technical term for that actually is rectangular form. So let me just write that somewhere here. So what we've got is we've got this complex number here, 4 plus 5i. Okay, and what we're going to do is we're going to convert that to what's this thing called polar form. So just a little bit of terminology. Okay, this form is known as rectangular form. Why is it called rectangular? Mainly because if you actually did plot this thing on the Argand diagram, let's do that very roughly, let's say that there, and we draw a line back to the origin there. That's meant to be a straight line. Okay, what you can also do is form a rectangle around there, so that's why it's called rectangular form. Okay, so let's have a look then at how we can convert this thing to polar form. So what does that mean for a start? Well, in polar form, what we're going to do, if I go back to that set of axes for a moment, and let's actually plot this once again. Just use a different color. Go back to this rectangular form for a moment. So this is our imaginary and real axes. That point that we can plot by going 4 across and 5 up, we could also get to the same point. I'm just going to draw myself a line here. It's roughly okay. That will do. Not perfect, but it will do. Okay, this point here, I could also have got to that same point by starting with the real axis here, turning through an angle. Let's give that a label, let's call it theta, and then starting at the origin here, moving this distance along that line that's got that angle there so that you also ended up at this end point here. So again, you'd need to turn through a certain angle, starting with the real axis as your sort of baseline, turn through the angle and then walk that distance along there. So that's what polar form does. Now there's a little bit of terminology that goes with this. This distance that we walk along that line is known as the modulus, and it's typically given a symbol of r. So that's that distance along here, and this angle that is turned from the real axis, okay, this direction anti-clockwise, is known as the argument. Okay, so let's tidy this up, get rid of all this messy stuff here, and let's do this conversion to polar form. Okay, so let me just get this rubbed out, and we'll get that replotted in a more tidy form, and let's do the conversion. Okay, so let's get that blue color, will be fine. So 4 and 5 here. So to get this distance, let's get that because it's pretty easy to get using good old Pythagoras' theorem. So let's put our symbol r here, and let's do a little bit of working to one side. R should equal the square root of 4 squared plus 5 squared, coming from Pythagoras' theorem. So it'll be the square root of that, which is going to be 16 plus 25, okay, which is going to be the square root of 41. Okay, and because we're going to need to plot that at some stage, okay, well, I've already basically got it plotted, but let's just see what that distance is as an approximate decimal. That's around about 6.4 to 2 dp. Sorry, 6.40 to 2 dp. It's better to leave it in this exact form, but I just wanted to get an approximate idea of that distance there. Okay, now what about this angle here? Okay, this is known as the argument. So how would we calculate that? Well, here we've got to use a little bit of trigonometry. Okay, and I'm using some right angle trigonometry. Let's just grab a different color here, and knowing that this length here is 5 and this is 4 means we can use the tan ratio. So the tan of that angle is the opposite side over the adjacent side using right angle trig. So that's going to be 5 over 4. Now you need to work this out in radians. That's the preferred unit for angles here. So I'm just checking my calculator is in radians mode, and indeed it is. So I'm going to go the inverse tan of 5 over 4, 1.25, and that is 0.896 radians. 3 dp. So if we put these two things together, let's just do that down here. If we call this complex number just z for a moment, let's just give it a label, 4 plus 5i, that's rectangular form, that is equal to root 41. And how do we write that in polar form? Well, the way that we write that in polar form is as so: CIS and then this angle. Now you may be wondering, what the heck is CIS? So let me try and explain that. Okay. Okay, so what the CIS is coming from is this is actually shorthand for the following: root 41 times the cosine of 0.896 plus I times the sine of 0.896. And where does that come from? Well, if you have a look back on our triangle here, this opposite side, if we just go over here to one moment, and we looked at the sine of this angle, well, that's the opposite over the hypotenuse, and the hypotenuse is r. So the opposite side can be calculated as r times sine theta. And so this distance O here, in this particular case, is going to be equal to r, which we know is root 41, times the sine of that angle, which we just calculated as 0.896 radians. Now if we also looked at the cosine of that angle, going back to this triangle here, that would be the adjacent over r, making a the subject of this. You'd have r times cos theta. So in this particular case, A would equal root 41 times the cosine of this angle. Now, we know that the rectangular form of z is equal to that real distance 4 plus the imaginary distance 5i, but in polar form that distance 4 units across here is the same as a, and so a is root 41 cosine 0.896. Now if you calculate that, you'll get 4, and this opposite distance here, well, that is root 41 the sine of this angle, the argument 0.896. And if you calculate that, you end up with 5, and let's not forget I. Now if we take root 41 out as a common factor of those two parts, we end up with this. And that is the proper polar form. So this is polar form. Now we usually write this in shorthand form, which is what I mentioned over here initially. So we've got root 41. Instead of writing cosine of this, we write c. Instead of writing the sine and I, we put CIS. So that is coming from that letter. That's for the C, that's the I, and that's the S. And then we put the argument here in brackets next to that CIS. But this is simply shorthand form for this, and that's really important to know, that this really is meaningless unless we know its shorthand form for this here. Okay, and so coming back to our question, convert to polar form, this here would be the acceptable answer. You can write it like this if you wanted to, but this is perfectly acceptable and the more really accepted form of the answer in polar form. And plot it on the Argand diagram. Well, we've actually got it plotted here already, and so you can see that it's a lot easier to actually plot in rectangular form. So quite often, if we wanted to actually plot something like this given in polar form on an Argand diagram, it's actually a lot easier to convert to rectangular form and then plot. So how would you convert to rectangular form? You'd write it in full form like that, grab your calculator and calculate these bits, and then figure out what the real part is and the imaginary part is. Remember, this here would be the real part, and root 41 times that sine value would be the imaginary bit. Okay, so that's really what polar form is. Okay, so there'll be some material I'll get you to read also from the workbook, and then I'm going to get you to try some questions where you actually are converting to polar form like this one here, and then plotting on the Argand diagram. Okay, so good luck with that. Refer back to this video if you need some assistance with those questions, or you might better catch me in class.